Ladies and gentlemen, welcome to tonight's All Space Considered. I'm Dr. David Reitzel, and joining me as always is Patrick So and Chris Butler. That's our All Space panel. But tonight, we're also very happy to have Professor Jeff Blake with us from Caltech to talk all about the James Webb Space Telescope. So let's all welcome Jeff with us. Tonight, we have a really very exciting show. Let's get right to that. First of all, we are going to begin with Professor Jeffrey Blake and exploring the cosmic web. So a little bit of a pun that's definitely intended there. And then we'll move on to our pretty pictures and solar system weather with Katie, who's going to join us as always. Got some really great stuff tonight. And we'll do some headlines. The Decadal survey that we mentioned last month, we're going to talk a little bit more about it. What was decided? What direction do astronomers think we should be going? And then Patrick is going to talk about Juno and Perijove 37 out at Jupiter and find out this time if any pictures that are worth taking a look at were picked up. Of course, I jest, all the pictures are gorgeous that have been taken from there. And what's always great is seeing how people have worked on those to bring out those gorgeous details. So Patrick's going to show one that would look like to our eyes and then another one that's been enhanced. And the difference is amazing. So you're going to want to catch that section. I'm going to talk about a little bit of news from Mars. Indeed, Perseverance and Ingenuity are still there. Curiosity is still doing things. So a little bit of news from there. And then Patrick's going to come back, tell you what to look at in the sky in December. And then we're going to end with Chris Butler being out to launch, as he always is, each month. And we've got a lot to talk about, a lot of launches that are happening. So got a great show tonight. First of all, I was recently away. I was here at this location. This is an observatory, another one that has an amazing view. And maybe you don't recognize that. Maybe this makes it a little clearer. I was standing at a particular line, and one foot's in the east, one foot's in the west, actually. And indeed, I was at Greenwich Observatory in London, and this is a picture of their famous refractor. It's a 28-inch there. That's a very large refracting telescope, by the way, at 28 inches. The largest is the Yerkes at 42. The Lick is behind it at 36. And then I believe this one might be the next one down the line, if I remember correctly. It's either fourth or fifth. And then, of course, the one down at Lick, not Lick Observatory, the one down at Lowell Observatory is a 24-inch, of course. That's a very famous refractor as well. So if you like seeing old telescopes and you happen to find yourself at any of those locations, check them out. This is the business end of it. They did not let me look through it. It was during the daytime, and I didn't let them know I was even there, although they were very impressed by Griffith Observatory and excited to talk about it with me for a little bit. So, and I want to take the moment here to talk about tonight's show and how it is brought to you by Griffith Observatory and not Greenwich Observatory. It's owned and operated by the Department of Recreation and Parks, which is run by the city of Los Angeles, of course. And we also want to thank our nonprofit partner, Griffith Observatory Foundation. If you're on YouTube, you're going to notice that we're still running a fundraiser to help our foundation carry out their mission, and their mission is to support Griffith Observatory and our mission. So hand in hand, we're able to bring you shows like this one tonight. So we appreciate all the donations that people have been making. So now, last photo, I didn't just spend time at observatories. I did a little time traveling while I was there as well. There's a fun theater presentation that lets you do it. They didn't let me take a lot of pictures, but they did take my picture outside of the TARDIS, which I thought was pretty great. I know that's one of your favorites, Patrick.
Absolutely.
You love Doctor Who as well, but let's bring it a little bit more down to earth and talk about why we need space telescopes and why we need to go to space. Maybe not in a TARDIS, but Earth has something that makes us want to go up there. What is that?
Well, okay. Well, actually, it is. Let me get the slide. It is this beautiful picture here. I mean, why do we put these? Why do we put space telescopes? I mean, why do we put telescopes in space? Well, it's all in this picture here. This picture is of our Earth, and it shows that beautiful atmosphere that surrounds the Earth. The atmosphere that sustains all life here on Earth. And just to give you an idea of the scale of how big the atmosphere is, if you imagine the Earth is represented by an apple, the skin of that apple would be the thickness of Earth's atmosphere. Now, the atmosphere protects us from damaging effects of space radiation. So certain wavelengths of the electromagnetic spectrum are reflected and absorbed mainly by the gases in Earth's atmosphere. Among the most important being water vapor, carbon dioxide, and ozone. And this absorption can be represented in this diagram that we see here. At the bottom of the scale there, we see on the left, there's a wavelength scale. On the left is the short wavelength radiation, and then on the left goes all the way down the scale to the long wave radiation. And then on the left there, you see atmospheric opacity. That's the amount at which these wavelengths are absorbed by the Earth's atmosphere. And there are certain windows, so we call this an atmospheric window, where certain wavelengths can get through. So we see that visible light, that spectrum there, goes all the way down to the ground. Otherwise, if it doesn't, then we can't see anything. So visible light reaches to the ground. Radio waves go down to the ground as well. And that's why we have observatories that observe in visible light, optical observatories, and radio telescopes. And all the other radiation, the gamma rays, the X-rays, ultraviolet light, which is really harmful for us, and most of the infrared part of the spectrum is absorbed by the Earth's atmosphere and doesn't reach the ground. Now, that's good for us, but it's not good for gathering information from distant celestial objects that emit this type of radiation. It just so happens that the James Webb Space Telescope is designed to observe in the near infrared and mid infrared range. And as you can see there, those fingers of absorption of infrared radiation does not make this telescope useful if it's on the ground. It has to go above the atmosphere and into space to be able to observe this infrared radiation from distant celestial objects. The JWST actually fills in the gap between the Hubble Space Telescope, which observes mainly in ultraviolet visible light, of course, and near infrared, and gives us those beautiful pictures that we've been seeing for years, and the Spitzer Space Telescope, which observes in the far infrared. And we don't have a space telescope at this time that observes in the near infrared or the mid infrared. And this is where the James Webb Space Telescope fits in perfectly. And this is going to be an exciting moment when it begins to observe in this region of the electromagnetic spectrum and give us some really spectacular imagery and results for astronomy.
Patrick, thank you for that. And very interesting look at, like I said, the sort of reason we have to go into space. The atmosphere blurs things out, of course. It's hard to look through, but not everyone knows. It literally just blocks certain wavelengths from our view altogether. So what is the history, though? We've known this for a long time. We've known when we point certain cameras up into the atmosphere, we don't see anything. We don't see stars. We didn't see a thing. When was the first time we put up a camera, though, that took a picture in one of those wavelengths that the atmosphere blocks? Chris, I know you're going to tell us a little bit about the history of this now. And when did this all begin?
Yeah, actually, this started even sooner than I expected. I knew that this was part of the birth of the space age. But I'll tell you, this picture here, this is the first photograph taken above the Earth's atmosphere in space, although not by an orbiting spacecraft. This is a sounding rocket. Took this picture in 1946, our first look down at the Earth. But even in these days with the sounding rockets, one of the things they did was include sensors to monitor things like radiation of different wavelengths. And they confirmed everyone's expectation that, yes, there are types of radiation that don't reach the ground. In particular, X-rays were one of the things early sensors were finding. And even in these days, in the late 1940s, they were detecting X-rays up there, but often they couldn't locate exactly where they were coming from. They needed more sophisticated instruments to do that and to actually have them be spacecraft in orbit, an orbiting observatory. One of the very early ones followed up on that X-ray detection, and that's a satellite Uhuru. You may think of Lieutenant Uhura from Star Trek. It's from the same word, it's Swahili for peace. But the Uhuru satellite, this is from 1970. This is when we were still landing on the moon. This is a long time ago, but it was an X-ray satellite and immediately made very important detections. Above the atmosphere, it was able not only to find X-rays coming from deep space, but to pinpoint where they were coming from. And they focused their attention on one part of the constellation of Cygnus, and then later, other telescopes, even on the ground, were able to triangulate in on what Uhura was detecting, and they found out that this was the first black hole. That was when we found them, and we found them with the aid of the Uhuru satellite that found the X-rays. That was the smoking gun that proved it was a black hole. And remember, those X-rays couldn't reach the ground at all. These satellites and spacecraft were going to be incredibly important in finding out things about deep space. There's many of them. As a matter of fact, I cannot begin to give you a comprehensive list of all, but here's one I bet you don't know about. This is the only time a deep space astronomical observatory was operated by human beings far off of the Earth. On one of the moon missions, Apollo 16, they actually brought a far UV camera with them. You can see it there in the picture. Remember from what Patrick said, far UV does not get through the atmosphere. So they were able to shoot pictures of many deep space targets, the Large Magellanic Cloud, all kinds of things, and the Earth, which is the picture you see right there. Another example, we talked about infrared and how critically important that is. Infrared doesn't get through the atmosphere. Well, this satellite, the IRIS, or Infrared Astronomical Satellite, launched in 1983, made the first all-sky maps of the sky in infrared light, something we couldn't detect from the ground at all. And there were plenty of important discoveries that resulted. Infrared telescopes in space have a long history. The Spitzer Space Telescope, sadly no longer in commission, was a very important one. And there'll be plenty of others. This is a band of the universe we want to learn a lot more about. And sure enough, the James Webb Space Telescope can help us out there as well. Hipparcos may be one you hadn't heard of. This one was launched in 1989. It was doing a very different thing, not dealing with wavelengths we couldn't see, but the sharper pictures that being above the atmosphere allows telescopes to pinpoint with very high precision exactly where stars are. And with a combination of different tricks, they were able to not only produce good star maps, but also to determine the distances to stars with a degree of precision far beyond what we can do on the Earth. Now, this satellite's no longer in operation. However, there is today the Gaia satellite, and the Gaia Observatory is producing even better, in fact, far better maps than the old one I was just showing you. All right, let me jump to the next one here. Here's a famous one for you. Hipparcos you might not have heard of. You sure have heard about the Hubble Space Telescope. One of the reasons you've heard about the Hubble Space Telescope, it shot so many amazing pictures and also shot them, yes, a little bit into the UV, but especially in the visible bands. And so the pictures were just outrageously accessible to everybody. The pillars of creation. We all have seen lots of these beautiful, beautiful pictures. But Hubble is now, although still operational, just about at the end of its lifespan. It's critical to get another telescope up there that can do similar things. And the JWST is the successor to this very famous space telescope. Looking at the sun, you might not expect people would put things in space to look at the sun. We can see the sun, but remember, we can only see it in certain wavelengths on the ground. And we have that annoying thing called day and night. You can't see it all the time. But if you put an observatory far from a planet, you're almost never going to have something get in the way so you can observe the sun continuously. This is the Solar Dynamics Observatory that you saw a beautiful video from in our opening tonight. X-rays are another example. I mentioned Uhuru. There have been plenty of successor telescopes in the X-ray and gamma ray band, all of these very, very high energy bands. And this is the Chandra X-ray telescope, which is still operational today. The Kepler Space Telescope, I'll leave you with this last one. This one is famous for looking at one patch of the sky for a very, very long period of time in its main mission. Again, that's a trick you can only do when you don't have a turning Earth and day and night. And these long observations with a very crystal clear view outside the atmosphere allowed Kepler to detect, not image, but to detect the presence of thousands of other worlds around other stars, exoplanets. An incredibly important mission. And this is being followed now by telescope or observatories like the Transiting Exoplanet Survey Satellite, or TESS. And indeed, all these detections are going to be passed on to telescopes like the JWST to do follow-up work on. The important point I want to make is that this isn't something that we did once in the past. And it's also not something we're just doing right now. Putting observatories in space is something we've been doing since the first days of space exploration, and I promise you it's going to be an important part of the future out as far as we can see. Thank you, Dr. Reitzel. That's at least a glimpse of a few of the space observatories.
Yeah, I appreciate your dive into that, Chris. Pretty amazing look at what we do. And like you said, it's just the beginning. They're launching a new X-ray telescope, in fact, that you're going to tell us about in the out to launch section, about a brand new one that's going up there. Many nations have deployed space hardware to make observations. Of course, the Chinese, the Russians, the Japanese. Hubble itself is a multinational cooperative event, as is the Webb. A lot of nations are helping this happen. In fact, that's one of the reasons it's launching on an Ariane 5. That's the European contribution to getting it up there. So these are exciting times for humanity, and it's really a lot of fun. And speaking of a lot of fun, we are thrilled to welcome our guest right now and to get started. So welcome, Jeff. We're thrilled to have you here tonight to tell us all about the Webb Space Telescope and its capabilities, a little bit about the history of it. But first, you tell us about yourself as well. And welcome. Everybody give him a round of applause. So thank you for joining us.
You're welcome. Thanks so much, Dr. Reitzel, and thank you also to Patrick and to Chris for that great sort of scientific introduction about why we're all so excited. And thank you to everybody who's tuning in live tonight on a Friday night. And those of you who might view the episode on YouTube over the weekend or later, it's going to be, hopefully you'll learn a bit and we'll entertain you some, and you can learn some new things. So yeah, I'll do a little bit about myself. So these slide decks mostly comes from the mission itself. So I'll be lucky enough to use the JWST, hopefully, starting next year. But first, I'll tell you a little bit about myself. So I am a Air Force brat. One of the important postings of my dad was in the Edwards Air Force Base when I was a youngster, and so I learned about technology of flight, and there was a base astronomer there. So I spent most of my life in and around Southern California looking at the sky, and you'll hear some great stuff later in the show about the things you'll be able to see in our skies in the coming months. And so stay tuned for that. It's going to be great. I'm also a new grandpa, so that's been great, and it really helps motivate me to do events like this to help people learn about why we love to do astronomy, and I hope you love to learn about astronomy as well. So what my group does at Caltech, I've been there since 1987. We look at the formation of stars and planetary systems, and one of the things, as I'll tell you, Webb is going to do for us is that we're going to be able to look at objects that are very cold and very dark, where they're not luminous in the optical. So you can see these beautiful young stars, just sort of blue stars and a globular cluster there, MGC 6723. And the dark patch off to the lower left is not empty. It's full of gas and dust that is actively making new stars, but we can't see the process using wavelengths that our eyes are sensitive to. But with things like Webb and other instruments at the radio that we heard about from Patrick, like the ALMA telescope in Chile, we can now make these beautiful images of young stars. And this arrow points to, this is a young star with what's called a circumstellar disk around it that we'll talk about in a little bit. And that's the circumstellar disk is what forms planetary systems. We can image those things now, as I'll show you. And Webb is going to tell us about how the young planets acquire really critical elements like carbon and oxygen that enables the planet to be habitable. So it's a really exciting time for us in astronomy. As we heard, we've been waiting for Webb for a while. The development cycle started back in 1996. It's been about 25 years since we got started on the technology to enable JWST. So let's think a little bit about the telescope itself and the kind of science it's going to do, and then we'll show you a really neat video at the end from the observatory members themselves about the audacious engineering challenges that the deployment of Webb is going to face. So as we've heard, Webb is an infrared telescope, and so I'm going to tell you a little bit about the telescope itself and the science first. Here's a sort of artist rendition of the deployed telescope with the thermal shield below it and the electronics that talk to Earth on the very bottom there. But here, for a sense of scale, right, this is a truly audacious instrument, right? So the scale bar here are humans down there in the bottom, right? It's a 6.5-meter telescope in diameter. It's gold because gold reflects infrared light very well and emits very little infrared light if it's cold enough. And so this big telescope is going to let us collect photons from objects at the very edge of the observable universe, for example, for the first time. So you can see how big this is. And the problem is, when we saw the picture of the Solar Dynamics Observatory, that was also a big telescope, but it was all one monolithic unit, like the Spitzer Space Telescope. Webb is so large, it will not be able to fit in even the Ariane 5 fairing without being folded up. And so in this image here, you see, again, for scale, right, still quite large, right? It's a couple people in diameter and much, much longer, but the telescope literally has to be folded up, shipped off to the launch site, and as we'll see in the video, when it leaves the Earth, it has to be unfolded again to do the science it's designed to do. Let's think a little bit about what that science is, and then we'll get to the video here. So I'll tell you about what we hope Webb will do, why the infrared is the right way to do it, and give you a few examples, and then we'll show you the audacious engineering that has to go in for the mission to work. So what Webb is really all about, and what's exciting to us who do astronomy, is that it's about our origins on all scales, both in time and in space. And so we'll look back, as I said, to the very edge of the early universe, when galaxies were first assembled, how those galaxies and the black holes inside them grew over time and distance. And then in our own galaxy and nearby environments, we're going to be able, for the first time with JWST, to learn about the chemistry and the growth of compounds and materials that not only create planetary systems, but potentially lead to habitable worlds outside of the Earth. And so we'll give you a quick little snapshot into each of those in a minute. But first, why the infrared? And so we heard stars are the fundamental unit of astronomy. Stars like the sun emit wavelengths mostly in the visible, but some into the near infrared. But because of this dust we talked about very briefly in these beautiful dark clouds, starlight gets absorbed by that dust, just like sunlight gets absorbed by haze in the LA basin. You know from driving around or walking around on smoggy or marine layer days, as the sun sinks towards the horizon, it becomes redder and redder, and that light gets scattered and absorbed by these small particles in the LA basin case in the air. But in astronomy, it's the clouds that seed the formation of stars and the formation of planets. And so we can't see through that material in the optical, and so we have to go to longer wavelengths. Radio is good, but as we heard, right, as the longer in wavelength it is, it's harder to make an image like you can with Hubble without bigger and bigger telescopes. And so JWST kind of splits the middle, where it's a short enough wavelength to have beautiful imaging quality and make spectacular images, but also long enough to give us access to these unusual environments and all stages of how stars and planets are put together. And so the infrared is important because it can penetrate these, as we'll see, just to give you a little sense for an everyday occurrence of visible versus infrared light. Here's a visible light image like our eyes would see of meerkats on the left and freshwater crocodile on the right. And in the infrared, what you see, this is on the same scale, so it's about the same size and it's the same scale. And so the meerkats are warm-blooded. They're higher in temperature than the freshwater crocodile on a cool day. And so the infrared gives us information not only about how much stuff is there in astronomy, but how hot or how cold it is. And because cold environments are really important to how we make stars, so I'll show on the next page, right? We really care about being able to see deeply into those environments. So there's a visible light image on the left, a near-infrared image, and then a mid-infrared image like JWST will do on the right. And you can see in these beautiful pillars of creation that those dark clouds that obscure light from behind them, but we can see through those clouds by going to infrared radiation. And the big challenge for Webb is that we care about these objects that are very, very far away. or that are very, very faint and nearby, like exoplanets. And so the job of the James Webb Space Telescope is to capture those infrared photons from objects very far away, or ones that are very dim, even locally, and to image them with superb quality, just like the Hubble does. So, for example, to show you a difference in what's going to happen, if we zoomed in on one of the little blobs in a picture like this on large scales, the Spitzer Space Telescope would have seen the blob at left, right? There's this one little blob there. But what JWST will do, like Hubble could do, but now in the infrared, is give us these gorgeous detailed images of galaxies and planets and nearby stars. And so it's going to be an extraordinary advance. And it's important that it's not just that it's big, it needs to be big to have sharp image quality, but it needs to be cold. And that we'll get into in just a minute when we talk about the engineering. Okay, so what will Webb do, just real quick, just to run you through. So just like, sorry about that, just like Hubble, here's a model taken from Hubble images of staring very deeply into space. You see all kinds of galaxies, even in very dark parts of the sky. And what Webb will do is, because as light comes from farther and farther away, it's stretched in wavelength. It's called the redshift. That means that optical light back at the dawn of galaxies is shifted into the infrared band where Webb does its work. And so we'll be able to look from right here to left at galaxies just being assembled at the early epochs of the history of the universe to more mature galaxies now that are in the local universe. And we'll be able for the first time to see that complete sequence of assembly of galaxies. And by doing what's called spectroscopy, which we'll get to in just a second, we'll be able to look at whether or not those young galaxies being assembled have active black holes in their centers or not. So it'll be the first time we're going to be able to watch the coevolution of stars and black holes over cosmic time. Near to us, again, we're going to be able to look at these creation environments where stars and planets are born for the first time. In the solar system, we'll be able to take beautiful images of our own planets at wavelengths that our eyes can't see, and we'll be able to look deeper into the atmospheres, for example, of the gas giants, or Uranus and Neptune. Or once it's discovered, we'll be able to take images of Planet 9, for example, even hundreds or thousands of times the distance of the Earth to the Sun away from us. And finally, on the science side, it's a beautiful image from the Keck telescope on top of Mauna Kea in Hawaii, where we block the light from the star, and you see these three little dots of light around it to the right. Those are exoplanets orbiting this star at a distance of about 60 or 70 light years from the Earth. Webb will be able to do the same kinds of measurements by blocking the light from stars and image young planets around nearby stars by using what's called a coronagraph. It's going to be a really exciting capability that was added to the mission, after many years of development of the appropriate instruments on the ground and by the JWST team at NASA and the aerospace companies. And the key thing about this, just to conclude, is that what we do is not just take images, we disperse the light, just like a rainbow, right? So they have instruments on JWST that disperse the light like happens in water droplets in a rainbow. And by looking at different colors of light, but now in the infrared, for example, here's the spectrum of the Earth, you can look at the compounds that exist in the atmosphere of this exoplanet and try to understand, does it have liquid water on the surface? Does it have oxygen? Does it have water? And so it's going to be a really exciting time where we're going to follow up the beautiful discoveries of Kepler and of TESS and ground-based surveys to actually take spectra of these atmospheres and try and decide if they might be habitable or not. And it's going to be an extremely exciting time for that community, and I'll be involved in that as well, along with the young planets and stars. So just to conclude here with a little bit of telescope in a movie. The telescope, again, is audacious. Here's the scale bar again. It's huge. It's 6.5 meters again, and it can't just be deployed. So you see on the right-hand side, again, the fact that the telescope has to be folded to fit inside the fairing. Here's a scale bar for how big it is compared to Hubble. So the Hubble mirror is at left. The JWST mirror is at right. It's made of these individual hexagon panels in a honeycomb shape that has to be unfolded to work. It's going to be launched out to a place called the outer Lagrange point. So the Earth and Moon are in the middle of the plot here. Where Webb is going is off to the right. And it'll orbit this semi-stable region called the Lagrange point, where it's very easy for it to maintain that stationary position relative to the Earth, talk to the Earth easily, and do the science it's going to do. The key thing for getting cold is you have to block light from the sun. So there's got two sides to the instrument. There's the observing side where the telescope is at left, and that's the cold side. This sun shield, which is layers of mylar, as you can see in the middle there, in between the telescope and the electronics that talk to the Earth, is meant to have a hot side facing the sun and a cold side facing away from the sun. So JWST the telescope will always be in shadow and in darkness, and that allows it to cool in space down to temperatures of only a few tens of degrees above absolute zero, and make it not just a beautiful imaging telescope, but spectacularly sensitive because we're above the Earth's atmosphere, as we heard.
This is a science mission
Now we're going
on
to look at a
par
video
with the
from
Apollo
the
missions,
observatory
Space
that
Shuttle,
talks about how
International
the
Space
telescope
Station, and
is
Hubble
enjoyed.
missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time, almost 14 billion years, to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
Thank God.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you, shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks. This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our Huygens antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet, then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers of approximately 8,900 square feet, almost the size of 3 tennis courts, a very thin Kapton material, about 1 to 2 thousandths of an inch thick. Making them go where you want them to go in zero-G is extremely challenging.
The sunshield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sunshield under control as it unfolds. First, we release these special restraints that protect the sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy aside. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sunshield release mechanisms need to fire on cue. 107. They free the 5 sunshield layers, allowing them to extend as the mid-booms deploy.
Sunshield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, a secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
I hope that video gave you a good sense for the amazing sequence of events that's going to have to happen fairly soon. So we're going to hear about Perseverance and Curiosity fairly soon. And that's called 7 Minutes of Terror by my colleagues at the Jet Propulsion Lab that work on those rovers. They call this 29 days on the edge, as you saw, because it's going to take about 29 days for the telescope to be deployed and become operational for testing. The first images will come back in about 3 to 4 months. So if all goes well, we'll have the beautiful first release images from Webb by about May of next year. So stay tuned for that. And if you have any questions, I'd be more than happy to
Yeah.
with you for a bit.
Yeah, thank you for the wonderful presentation and that amazing video there. It was great seeing Amy Lowe. I was at UCLA with her as well. She was a lot of fun there and one of our contacts there at Northrop
It's an
Grumman.
amazing team.
Yeah, the team is incredible that put the craft together. We were lucky to go visit it and get a quick look at it while it was being built as well a couple of times, and it's enormous. It's hard to picture how very huge that primary mirror is until you see people out on devices, and it was crazy. So everybody's on edge about this and worried about the launch. We do have some questions. I saw one in our chat that was asking about when it's out at L2, what exactly is it orbiting? And one of our staff members said it's actually orbiting the Lagrange point itself. But why is that? Why is that a stable place to be? And what is that orbit about?
It's what's called a quasi-stable place. If you were exactly at the Lagrange point and you could perfectly stay there and there were no changing forces on you, you would be stable at that point. And so what all these telescopes are going to do, and JWST is one of the first, is that you will orbit around that Lagrange point in these sort of infinity symbol or figure 8 orbits, where it takes very little thrust to maintain a stable orbit around the Lagrange point. And so what that means for Webb is that it has to have a very carefully designed sequence of observations, right? The sun shield has to be in the right orientation to shield the telescope. There's only certain parts of the sky you can look at any given time and maintain that orientation. And because the structure is so huge and it's in space, if you slew it too quickly, it will sit there and just kind of oscillate and not have very good. And so they've had to, so the whole reason that the first call for proposals came out over a year ago was that so the engineers had enough time to plan the sequence of observations so that you could maintain this quasi-stable orbit around the Lagrange point and conduct science observations. That's a great question.
Yeah, a follow-up from me on that. Since one side of the spacecraft is cold and one side is warm, will there be any thermal pressure that's put on due to the heat differences? I know asteroids will spin up due to effects like that.
Yeah, and so depending on the orientation, the slight ones, because in the slight different orientations, right, the shield will not actually be the same distribution of temperatures across the entire 3 tennis courts of the back. There's very fine guidance sensors that look at stars on the spacecraft and actually have to use a little bit of the fuel to make sure that the telescopes point exactly where it's supposed to. So yeah, we'll have to adjust to the fact that there's changing solar insolation, there's changing attitude, and so yep, it's going to have. Fortunately, it's so efficient at L2. A very modest amount of fuel compared to, example, what Spitzer used will last the telescope for 3 to 4 decades. So fuel is not the main limitation.
You just touched on a point there. You said 3 to 4 decades. How long is the projected lifetime of the JWST?
It's called the phase 1 or level 1 mission requirement is 5 years. But unlike the Spitzer Space Telescope, right, for the Spitzer Space Telescope and IRAS before it. So again, thank you to Patrick and Chris for that nice introduction. They carry what's called liquid helium. So it's helium atoms that are cooled to about 4.2 degrees above absolute zero. And as they boil off, right, that cooled the telescope and the instruments. But once the helium was boiled off, then Spitzer warmed up. So on Webb, we actually use little mechanical coolers that do that for us. And so there's no cryogens to run out, but these are active coolers. And so if those fail, then the telescope will begin to warm. It'll be colder than Spitzer was because of the sun shield, but there'll be certain capabilities that will be lost. And so I suspect, perhaps like Spitzer, right, the longer wavelength instruments will probably go first, and then the shorter wavelength instruments, because remember, I didn't say it, but the Webb telescope actually works down to near optical wavelengths, and so those instruments don't need to be so actively cooled as the long wavelengths do. So,
So it could be
Another
quite
good
a bit longer than the 5 years. We just don't know
Yes,
how long.
hopefully. We hope so. We hope it's going to be like those wonderful, rovers on Mars and go way past the mission lifetime, like Spirit and Opportunity.
Absolutely, we really are. Some folks were wanting to know what the Lagrange point really is, and a simple answer is it's further away from the Earth is the one they're going to. So you would think an object there would take longer to orbit the sun, but you need to add in the Earth's gravity as well. So the sun's gravity plus the Earth's gravity create enough tug to accelerate the spacecraft out there at the same rate to go around the sun in 1 Earth year. So it's kind of a balance point out there. There's also one interior where the Earth's gravity is subtracting the extra gravity because you're too close to the sun, so you'll orbit the same rate. And there's one ahead of our orbit and one behind our orbit. Those are the 4 well-known Lagrange points. In fact, we think there are asteroids clustered at the L2 and L3 forward and backward in our orbits, and we've only found a couple of them because it's really hard to find them around Earth. Jupiter has
found them
lots.
around Jupiter.
Yeah, in fact,
so that's another Lagrange.
That's where Lucy is going.
Yeah, the Lucy
exactly.
mission is going right there.
We'll hear about Lucy coming up.
Yeah, Chris will tell you a little bit more about that launch and how that.
The Genesis spacecraft was at the interior Lagrange point and collected solar wind particles to learn about the composition of the sun. That was another great mission that was astronomy related, but collected actual samples.
Yeah, we've got a great question here wanting to know if the Webb will be able to see the bands of the atmosphere of gas giant planets. So first of all, in our own solar system, will it be able to see that? And then will it be able to tell us anything about bands of clouds in gas giants around other stars?
Another excellent question. So yeah, Webb is big enough that it'll take spectacular images of planets in our own solar system, but at wavelengths that are hard to do from the ground. It will let us see, for example, in Jupiter, you can see deep into where the water clouds are for the first time with these wavelengths. This will give us a whole new way to track dynamics on storms and circulation patterns, which we'll hear more about from Patrick in the Jupiter segment of the show. And for exoplanets, we don't actually resolve them, but what we do is, the exoplanets will spin just like the planets in our solar system do. And if you look at those planets over time, the light that's emitted by those planets varies slightly as the different cloud bands come into view or come out of view. And so by doing what's called time domain astronomy, then we can begin to learn about, what the cloud cover is. And then by doing this, again, dispersing of the light into a rainbow, we can learn about what the clouds are made of in those bands. And so the combination of doing spectra on those objects and watching them change over time will tell us about weather on not just exoplanets, but stars, brown dwarfs, things like that. So it'll be a really important thing that Webb will do, and where we really hope the mission lifetime will, as we heard, greatly exceed 10 years. So we have enough time to watch these things change and learn more about the objects.
Yeah, it'd be fantastic to know more about them. Another question, do we have a target for those first images? Do you know what the first images will be?
They have been selected, but they have not been released. One of my former students, Dr. Alexandra Lockwood, is the chief communication scientist for JWST, and these early release images the objects have been chosen, but they have not been revealed yet.
Well, this sounds like the sleuths out there need to get going because we have
probably do.
We know what time of year it's launching. We know where it's going. We know that the sunshade has to be facing the sun. So there's sort of a band that you can observe that time of year. So we ought to go see what's in this band. How long is it going to take to deploy everything? 29 days to get it out there. And then the first observation shortly after that. So about a month after launch, let's figure out where we are. We'll figure out what band is in there. And maybe Andromeda's right dead center of that band. And we'll know that's the target.
Well, do you have a favorite? Do you?
I know they tried to pick one from
different
images. So they've, I study young stars and planets. So I'm sure that one of these young stellar nurseries will be one of them, like the Pillars of Creation. And I'm sure there'll be an interesting galaxy out there, and there'll probably be something from the solar system as well. So we'll see. They really want to showcase all the different. So it's not just I should have said, there's not just one instrument on JWST. There's a near-infrared camera and optical camera. It can do spectra of many objects at the same time, and there's a mid-infrared spectrometer and camera, and both of these have these what are called coronagraphs that block the light from bright objects and look for dim things. And so they're gonna exercise all the modes of the telescope and demonstrate to the public and to the scientific community that all the modes are working, and show just that'll be these spectacular images. So.
Yeah. Well, will there be any really deep sky images taken, like the deep fields that Hubble took? That's another question from
Maybe not right away for those, but what they also have are early science observations, early release science, and those. So usually, the way these telescopes work is that you get to propose, you get your observations, you get to work on them for a little while before they become public. But for the early release science, those results will be released to the entire scientific community and the public immediately upon processing, and those will have very deep images and very large scale images. And so those will be, I guess, the one that people are really waiting for. These early demonstration observations are short, but the early release science is going to be spectacular, and we'll all get access to it at the same time, and the race will be on.
Yeah, so get those grad students and postdocs ready to start doing analysis and get those papers written. And then Patrick, you'll lead a whole team of people to probably make some just beautiful.
It's all out there, so I'm really hoping that people will combine, Webb observations with optical images and just make some spectacular data sets for us all to enjoy.
Yeah.
Will there be a public outreach site where you would post these images as they come in, and
yes,
people
so
can...
the early release science will have the raw data for the scientists, but then also processed images through the pipelines that are available to the public for easier use and consumption. So
yeah, that'll be fantastic. Now, somebody in our chat also wanted to know, will there be any cameras watching the Webb unfold during those 29 days? What will be the indications we know things are going well?
Yeah, I don't believe there are cameras on it, so it won't be quite like the Mars where we had these spectacular images of robots taking pictures of robots in the whole descent. It's just astonishing to watch that happen. So this will be a much quieter and more deliberate process, where it'll be telemetry from the spacecraft telling us when things are working well.
Yeah, I know they decided not to send any CubeSats or anything like that along to observe. A little too dangerous. You don't want to have a CubeSat go awry when you've got a telescope of this value going up.
Correct.
Here, people are hoping we look at Sagittarius A star.
I'm sure that will happen.
Yeah. And, I'm very much looking forward to a lot of the exoplanet observations that are going to be made possible with Webb, characterizing some of the nearby exoplanets that are in the habitable zone, being able to see, is there any sign of, say, water vapor? Are there clouds? Is there an ocean? And then starting to ask the bigger questions of, well, methane, you need to reproduce it. Sure, you can do it with volcanoes, but if you also see oxygen, you also see some of these secondary indicators, you start to build a case that says maybe something really interesting is going on here. And Webb may answer these questions to more detail than we think. As people get the instruments and they get the telescopes in their hands, we always think of new ways to use them. So we have all these ideas now what Webb will do.
That was the real lesson of Spitzer, right?
Yeah.
Spitzer was not designed to do exoplanet science, and it spent some large fraction of the Warm mission doing spectacular exoplanet science. And so you're exactly right. People are extremely creative, and so I just can't wait to see what we all do with the telescope.
Now, the latest on the launch is still no earlier than the 22nd of December.
Correct.
The last I heard, the reason that was pushed back a little bit from the 18th is there was a vibration in a bracket that held it to the vehicle. It came loose somehow. They were a little worried, but not too worried, because remember, Webb went through acoustic testing. It was put in a chamber and they sent loud sound waves through it, making the whole thing vibrate and shake to simulate launch. It was also put on a platform and shook to simulate launch. So a strap coming loose, although not ideal, it also was not the biggest vibration that the craft had suffered, and they believe everything is fine. They put it through what paces they could. They've checked what systems they can, and everything seems to check out. So we're on schedule to launch on the 22nd. So stay tuned, everybody. It's coming right up. And any final questions from you, Chris or Patrick, or from our audience out in the YouTube land? I'll take a look here. I'm not seeing any. So again, thank you so much, Jeff, for joining us. I very much
Absolutely.
appreciate it. It was
Thank you
fantastic.
so much.
Yeah, and
Thanks for the invitation. I love being here.
Yeah, well, next time, hopefully you'll be able to join us in person. Sooner or later, this pandemic will end, and Griffith Observatory will be able to have folks in person, and we'd love to have you come join us in the Leonard Nimoy Event Horizon Theater in person, get to see our audience in person. These are fun to do, and we'll keep streaming always. I don't think we're going to have a day we won't stream these any longer, but there is something nice about being at Griffith Observatory. It's a very special place, and we'd love to have you there.
One of my favorite places in all of LA.
Well, thank you for saying so. And again, wonderful segment tonight. Everybody, let's stay tuned. Keep the cat off my keyboard here. Stay tuned for that launch. So thanks so much. Here, once again, this is the sequence of everything that has to go right after launch. It has to get out there, fire an engine, unfolds all these steps all along the way to make sure that we end up with a Webb telescope that works. By the way, here's our faked. Of course, they wouldn't let us take pictures of when we went and visited the Webb telescope. Back, Dr. Danley was with us. I put on the bear mask. That's me in the background with my glasses and a bear mask. I'm not sure why I did that. Anyway, time to move on to some pretty pictures with Katie. Katie, there you are. Thank you for joining us. What do you have for us this month?
So this first image is a beautiful image actually taken from Sweden of a double winter rainbow. This is by Göran Strand. And then this is the moon on November 13th during a hike in Griffith Park. And then this is the full moon on November 19th from Sweden. So the eclipse was not visible there. And then some lovely images of Jupiter from left to right. We have October 25th, 26th, 27th, and then 29th. These ones are by Damien Peach. And then telescope demonstrator Anthony Perkic took this lovely image, I believe this morning or yesterday morning, of Comet Leonard. And then some beautiful layered bedrock sediments. This is on Mars. This is a beautiful sunset from Griffith Observatory just a couple days ago. And on that same evening, beautiful cloud layer that covered the city. And then this image is from Italy. This is a time-lapse image of star trails around Polaris, and then some clouds came in from the south, causing those beautiful colors. And to some clouds on Mars. These are called Mother of Pearl. And this was from the Curiosity rover Twitter page. And another one from Mars. These are noctilucent clouds. And then on to some space weather. This is a halo coronal mass ejection from November 2nd, headed toward Earth. And actually, a couple days later, we saw some aurora in California. So this is actually Lincoln, California, just outside of Lincoln, which is up near Sacramento. And then these are from Uranus as well. This is November 30th, so an active sun through the month. And then on the 29th, this coronal mass ejection occurred, and there was a geomagnetic storm watch for December 3rd, which is actually today. So this is a screenshot of the forecast, and this is the first all space where we actually have more than just that lime green color. So you can see a little bit of yellow in the forecast there. So hopefully we will see some more beautiful aurora images very soon.
Any of our fans out there in Siberia, if you happen to
that's what I was thinking.
Of course, Earth can rotate around, and looking like Greenland and Iceland might have gotten a show today, and who knows, maybe even the Upper Peninsula of Michigan. We'll have to see. But thank you for that, Katie. And I still want to get a trip to go aurora viewing. We need to plan this out for the future. Maybe we can get our foundation interested in this. some of our foundation members to go on a trip. I know they've done it in the past. It would be a lot of fun. Time to move on to a little bit of other news about the pathway to discovery in astronomy and astrophysics for the 2020s. What the heck does all that mean? So what I'm talking about here is the Decadal survey. It's a every 10 years, astronomers get together. A panel is picked essentially of people that are very active in research, and some of the best astronomers in the field decide what is the most important direction for astrophysics and astronomy to go. What mission should be launched, what gaps need to be filled, what do we need to be doing to engage with the public and also to engage with the science. And this was recently published, and we're going to go through all of these, not in detail at all, but you can see the sorts of things that the teams worry about. And the very, very top, let's break it down into what's going on here. Up top, we have the big goals. So that's what's important. What are we trying to do? We want to go find habitable worlds, other Earth-like planets out there. We want to take a look at worlds and suns in context, because planets don't just hang out on their own. They're around a star. And if that star, say, has too much X-ray flares coming off of it, it'll fry all the life. So we need to understand how the two evolve and work together. Also, it's important for Earth. Our own Earth is around our own sun. We need to understand how the sun works. We measure it every day, but a deep understanding of these environments is needed. Also, new messages and new physics. What are we talking about? Well, things like gravitational waves. How do we leverage those together with other thoughts at other observatories? So this is the stuff we're talking about. Deep thoughts of coordinating observations to get us the best new view of the cosmos. Now, in order to do it, you need to have some space-based tools and ground-based tools. You need to have the vision of the future to be planning things that are decades off. Again, the Webb was in the planning in the early 90s, and we're hoping to launch later this month finally. So, you know, these things literally do take multiple decades to pull off. Now, some of the science that's going to get done, again, the environment around stars. When you have stars just being formed, planets get formed then too. What are those environments like? What do the planets go through as this happens? Is there a reason why in our solar system we have an Earth-like planet where we do, but in other ones we have the gas giants closer? Was it due to something in the environment while Earth was being formed and the sun was formed, or did something else happen? We don't have a companion star as far as we know, but understanding how binary solar systems and how that affects the planets is very important as well. Sometimes the binary stars are very faint. Little brown dwarfs can swing in every once in a while and wreak a lot of havoc. We also need to understand how stars and galaxies and the gas within them interact. When stars evolve from molecular clouds, these are things, again, the Webb is going to study. We're going to learn more about it, but we need to have the plan for when we learn what Webb's going to tell us what's next. How do we take that information and leverage it further? So we're going to say these stars formed, supernovae are going to go after that, sends jets and winds, more material back out into space. It cools and gets recycled sometimes. We see evidence for flows, inflow in galaxies. But what does that really mean for the evolution of galaxies? We need to study galaxies throughout all of time to really be able to make these decisions and understand these processes. Like I was saying, also the multi-messenger part of it, where we take gravitational wave information, black holes that are colliding. Once we start to get a real family of black holes, and we know what rates different masses are accreting together and forming together, we'll have to figure out, well, how did they get that way? Was it pairs of stars? We're going to start to see galactic size black holes merging, or it'll be from dwarf galaxies that merge together and coming in together. In fact, there was a story I saw today about, I think it was Draco has a nearly 4 million solar mass black hole in it, a dwarf galaxy around our own. So what is that doing there? And what does that mean elsewhere? Well, our gravitational wave astronomy can tell us about that. But there's also neutrinos. We have neutrino observatories that work now, but they don't give us a great picture of what's happening. We tend to say we got a bunch of neutrinos from that direction. That's about the best we can do. And the direction isn't very precise. We need more precision, because when stars explode, they give off neutrinos. When black holes merge, probably not, but a black hole and a neutron star merging might give off neutrinos, and certainly two neutron stars merging creates all sorts of bling. We've talked about that one before. And also makes gravitational waves and neutrinos. So we can see all of this happening together. And then, of course, we have photons, good old light, good old-fashioned light in the infrared, in the UV. We need bigger telescopes to provide us even more details for that. And this is what the Decadal survey came forward with. And they told us that those are the important science topics, but we need to have great observatories in order to do great science. In the past, these are the observatories we had. We had Hubble, Certif, which became Spitzer, Chandra, and CRGO, that's the Gamma Ray Observatory.
Compton Gamma Ray Observatory.
Gamma Ray Observatory. So these were the 4 great observatories we had. And now we do have Webb coming, but it's not truly a Hubble successor. It works in a different wavelength range. It is designed to do a certain kind of work. It's not, it'll fill in certainly, and it'll expand our capabilities where we need them when we did, but we need these telescopes. These are the next ones we need. The exact design will change, I'm sure. These are concepts of how they will work, but Origins is going to be a far infrared telescope that's going to be able to look at literally the origins of stars and the origins of these things, and find things in the far infrared in some of the coldest environments where the action is happening. HabEx is going to look at habitable planets, actually go and resolve them and say, we're going to see these planets. And that means you can do spectroscopy on them if you've resolved the planet. It might not be more than a few pixels, but if you have it separate from the star, you can start to analyze those planets, and it'll do it much, much further away. By the way, Origins is supposed to be something like maybe a 10 to 15 meter telescope across. So that's not small. These things are small. Louvre,
tiny little thing.
Rover also is another one, looks very similar to the Webb design, but it will work in the ultraviolet, it'll work in the optical, and also in the near infrared, but we'll have a big shield like that to keep it cold and to protect it from stray radiation. And then lastly, Lynx, a brand new X-ray telescope to increase our sensitivity and the resolution. We need to get down in those AGN, active galactic nuclei, where the black holes are accreting material, and see where those X-rays are coming from. By combining all of these sorts of new great observatories, we can push the frontiers of science and astronomy into these sorts of territories. So we're talking about really moving things back towards the age of the universe, back towards the CMB polarization ideas. You do that with gravitational waves. You can't see past, the cosmic microwave background, but with gravitational waves, we might be able to get more information about what's going on inside of there. So these are the exciting frontiers they're talking about. They say, let's plan them now. Let's think about a giant array, a new array to be, bigger and better. Maybe put it on the moon. This is certainly a very fanciful diagram here, but new arrays to replace the aging radio arrays that we have now, ones with increased capabilities. We need new telescopes for a new ice cube telescope. That's the one that does neutrinos. So all of these working together will certainly expand our capabilities and certainly push things forward. Certif is already X'd out on this one because we no longer have Spitzer. Anyway, Webb is coming. It costs billions, and then we have all these low-cost missions that only cost millions, 300 million cheap, just like that, to send these ones. They also mentioned, this Decadal survey, that we should have medium-priced missions, ones that fill in that gap. It's nice to have a $300 million mission, but you have to lose capabilities to keep it that cheap. And it's great to have a $5–10 billion mission, but those you can't afford to do very many. So they suggested that they should fill in between these with handfuls of missions that maybe cost, $1 billion or $2 billion instead of tens of billions. So invest a little more, get more capability, but don't put all your risk into it either. So not all of it was about technology. Some of it was about the culture and the people that are doing the astronomy and doing the science. And it turns out if students start wanting to do physics and space, they usually don't end up doing math and physical science. They leave. They go into the social sciences. They go into biology. They go into humanities and other things. Now, the question was why? We're losing diversity. We're losing people that have an interest. And they felt that astronomers and physicists, we need to put an effort into understanding why that's happening and try and reverse it. Try and be more inclusive. We will be better science gets done when you have people coming from all sorts of different perspectives to do the work. It's not just about doing it how we always have done it. So that was an important point they made. Another point they made was we need to remove things like expensive projects that are not generating a lot of science. As much as I love Sophia and I love the notion of hacking a hole, well, a beautifully hacked hole in the side of a 747 and putting a Hubble-sized telescope in the side of it so you can get above a lot of the atmosphere. You can take infrared images that the water vapor will block. It's a great idea, but it's costing us as much as Hubble to run. We can't afford that. If folks want to run this, we need maybe some private consortiums to come in and run it. And that's the way forward, I feel, for that. But having a national asset where we're spending that much money on it, I don't feel is the way to go. And it was recommended that they cut it. Getting back to the point of these long viewpoints, you need to plan great observatories literally decades out. So they made some plans that were all the way out to the 2050s and said, this is the things we need to be looking at, pushing these developments way, way out into the distance. So that's just a broad overview of the ideas and concepts that are put into this. I was away for too long and didn't have time, certainly, to go into too many details on this. And also, things change. They really do. This is the recommendations. And Hubble was a recommendation that came out of a decadal survey. Webb was a recommendation that came out of it. So when we take these seriously, we're able to do great science. And I really very much hope Congress and our nation takes these recommendations seriously and puts the investment into these projects we need to have our next set of great observatories to solve the next great problems. It's how we stay at the forefront of astronomy and astrophysics. And I very much hope that we do. So stay tuned for where we're going to go on that, and we'll see more. But right now, we're going to come back to home, back to stuff that we've seen, and let's talk Perijove with Patrick. Patrick, what Perijove number are we finally on right now?
Right, we are at Perijove 37, and this is the Juno spacecraft. This is NASA's mission to study the planet Jupiter really up close. So Juno has an orbit that takes 44 days to go once around Jupiter, and its closest point to Jupiter as it goes around it is known as Perijove. We marked that as PJ, and the 37 is the 37th close approach of this spacecraft to Jupiter. At that point, the spacecraft is traveling roughly about 130,000 miles per hour, and it's just about 2,000 miles just above the cloud tops of Jupiter, and it has about 2 hours to make all its observations as it goes literally from the North Pole to the North Pole to the South Pole of the giant planet. And as it approaches the North Pole, it's taking images that cannot be seen from the vantage point of Earth and gives us a unique view of the polar regions and some of the atmospheric dynamics that occurs in this region here. And here we're looking right down very close to the northern pole, and you can see a whole array of detail there, these folded filamentary areas, and it started with cyclones. It's a very complex dynamic that's going on in Jupiter's atmosphere. This image, by the way, is color enhanced, so Jupiter's poles are generally this greenish, bluish color in appearance. In contrast, as the spacecraft moves further down from the poles into the temperate region, this is about 54 degrees north in latitude of Jupiter, you can see there are some color changes here. And again, this beautiful folded filamentary region there is disturbed by a cyclonic storm, kind of that brownish swirly pattern there that you see there. It's unscientifically expressed, but it's in detail. We can see this storm, and now that the sun angle is a little bit lower, we can get a sense of some of the profile of those clouds. There's shadows being cast from the higher clouds onto the lower clouds, and you can get a sense of the depth, almost like a three-dimensionality of this particular storm. At the bottom there, near the bottom center, you can see there was little white specks there. Those are pop-up cumulus type clouds made of ammonia ices. Another feature that was imaged much closer to the equator of Jupiter and very close, actually just about 2,000 miles above the cloud tops of Jupiter, is this swirly kind of storm, which is known as a anticyclonic oval. This is the first time we've seen this up close. Nearby, that brown spot is a barge. And in our next image, let's get a real close look at this. You see the edge of the storm, and then you can see the barge off in the distance near the horizon there. This is an image taken, kind of processed in true color. So if you're at the vantage point of Juno and looking down, this is what Jupiter would look like. And it's hard to discern some of the details there without color enhancing images, which the public have done wonderfully to really bring out some of these details. And you can see the waves and the edge of the storm there. And it's even dotted by those pop-up clouds, which form a little crescent around this cyclonic oval. Incredible picture. Another incredible picture that I haven't seen, but this is just about 2,100 miles above the cloud tops, is this picture that's looking towards the horizon. And here, I've not seen this, but this really amazed me. The edge of the atmosphere of Jupiter is visible. And this is the first image I've actually seen with that showing. So this is really beautiful. It almost looks like some of the artistic illustrations that we've seen of Jupiter. So it's incredible. Now, these are just a few of the images returned from Perijove 37. And to see more, just simply go to this website. It's at Mission Juno. And you can see every image, raw images from Juno and processed images done by the public. There are so many of them, and many of them have not been published by the media. So you're going to see some really incredible images have not been seen in the mainstream media. So it's a very delightful site. And we look forward to Perijove 38, which has already occurred, but we're still getting images from it. So I'll cover that next month.
Excellent. Thank you, Patrick. Always amazing images like that. And I'd never seen the edge of Jupiter's atmosphere like that either. To me, you know, I'm seeing almost some layering in there. There's certainly a profile of how it, it's pretty incredible. Pretty incredible stuff. So thank you. Now it's time for a little brief update about Perseverance, Ingenuity, and also Curiosity. We're going to bring you a little Curiosity today too. This is an older set of couple of images, but I do just love it. I love it. It makes it look like, hey, little buddy, there you are. Indeed, we do have a new rover there. Those of you that have been not paying attention to Mars, and it brought a helicopter with it. That indeed is a little helicopter with, anyway, it hops around, solar powered. It's just fantastic. You might wonder, where are they? Well, there are their locations in Jezero Crater. The yellow is actually the path that the helicopter took. So each of those little lines is a different hop. It's done now 16 hops to various locations. It has been actually pretty useful for Perseverance to be able to scout the terrain ahead of where the rover is going to go. And you might say, well, where'd the rover go? Oops, I'm messing things up here. Let me back it up here. First of all, the Ingenuity has been flying. Let's talk about the flight first. And you can see here a view down. You see the blades, or the lighter colored shadows there, and the darker colors, the body of the helicopter itself, the legs, the springy legs. And that's a shot down from the navigation camera on one of the flights. Let's bring an actual picture of the flight. Perseverance is able to see them. Do you see the helicopter over on the left-hand side? Well, I hope so. It's located right there. I don't know if you can see that. Let me get my laser pointer up. Laser pointer, and I'll circle our helicopter. There it is. And it's going to take off, start flying to the right here. It did a little spin. You see the legs spinning, and indeed, off it goes. So this was actually from the 13th flight. It was a difficult flight for Ingenuity. Flew higher and had to spin the rotors faster than it has needed to do in the past. The air is cooling down there a little bit, and I believe it's not summertime, so the atmosphere is not as dense that high up. So they're having to really move the blades quickly. And it also was a fast flight. They were testing some of the fast motion, and it was over some difficult terrain. So it comes back down. You'll notice, if this is the one that caught it, it does a little bounce when it lands. Yeah, did you catch that bounce at the end? Some folks wanted to know, why does it do that? And the answer is, they actually program it to land in a spot that's about a little bit further below the ground, because they don't want it to come in and have any ground effect where you get turbulence and it could get toppled over. If you come down and just hit one leg, you could pivot around that one leg. So it's kind of dangerous. You're better off coming down and landing with some authority, even if you bounce a little bit. So they do that on purpose. It's done to actually protect the craft. Now the rover, this is the path the rover's taken, and you can see it's been very similar than the path the helicopter took. It's not far from the helicopter. The helicopter's now going to head off back the direction it came and kind of head back towards the original landing site. Perseverance, this is the path that it has taken while it's there. Let's zoom out a little bit, and then let me show you the important feature here. This is that delta, that material that was dumped by what we think was flowing water. And right now, Perseverance is out in this region. Certainly, we think water flowed over this place too, but a lot of the rocks look like they were probably put down maybe by other processes. They might have been some of the original, what we call paving stones, where water flowed over it, but it wasn't deposited by the water, which is less interesting to the scientists. But they are still taking gorgeous images, of course, and we are seeing some evidence for layered terrain. Now, whether that terrain was laid down through the action of water and deposits in some sort of river, or this was laid down maybe by sand. It could be sandstorms and windstorms laying down dust over long periods of time. I'm not sure. This is why we're here to investigate it, but really neat shot from Perseverance. This just came down today. These are raw images. You can go to the raw image folder and just download them. Another shot of that kind of interesting looking layered-ish terrain there. It's amazing stuff to think that this is the quality of images we're getting from Mars, and the lovely tracks going off into the distance there. And remember, this is not a small rover. The wheelbase is about the same as a big SUV. The body of the rover is maybe the size of a Mini Cooper, but the wheelbase is pretty wide. It does not travel quickly, but it is making some distance. It's gone about 1.6 kilometers already. So making some progress on Mars, and yet still a ways to go. Did just recently take its 5th sample, doubled up on this one, high priority targets. They thought this rock was interesting enough to take 2 different samples of it. So now we're up to 5. We have plenty of sample containers still, so that's to come. We'll be taking more as we get to more and more interesting locations. Curiosity, stop selfie time. I took this 360 image. Well, Curiosity did. Maria Gordon Notch is that sort of notch off in the distance that Curiosity is going to head up and look over. Let me get my laser pointer back on. That notch right here, Curiosity is going to head up and peek over that ridge and see what's on the other side, and plan to continue to head up Mount Sharp that it's been going up. We're getting to more and more interesting terrain on Mount Sharp, because Mount Sharp was laid down through wind and dust filling that crater, and then has since been re-eroded. So it tells a story of Mars in ancient times, and we'll be able to see when was it wet, when was water involved, when was water not involved. So it's unlocking the past history of Mars as Curiosity climbs it. So check out that link. Make sure you stay in contact with Curiosity. A lot of fun stuff is going on there. It's time to move on from the Mars skies that you see there back into our local skies and find out what is up in the sky in December to see. Get together with your friends and family and do some observing of the sky. But Patrick, what should they look at?
All right, well, we'll start with this picture, which I took last month, but it's going to be similar here. There are actually, in the evening sky right after sunset, 3 planets that you can see all at one time in the southwest, starting with the brilliant planet Venus, and then the brightest planet, the second brightest planet in the sky, in the night sky, and that is, of course, there's Jupiter, which we talked about with Juno going around it and giving us all those fabulous photographs. And then in between is the planet Saturn. This is a really great time to go out in the evening and observe these planets. And amateur astronomers around the world have been doing that and taking some wonderful images, which we'll share with you. Here is Venus, and if you were to look at it, it looks like a crescent right now. It's a waning crescent. Venus is now moving in its inside orbit between us and the sun, and it's becoming a little tiny crescent. And today it's at its brightest, it reaches greatest brilliancy. Another object, of course, is the giant planet Jupiter, and here it's shown in with its majestic cloud bands and even little details such as the barges, those brown spots that you can see. This image comes from South Africa, and this image also was taken through the same telescope, a 14-inch telescope, showing Saturn and of course its beautiful rings, which are currently tilted roughly about 18 degrees towards Earth. And so this is a good time to actually see the rings. And even with a small telescope, even if you have a 16mm refracting telescope, you can still image the rings of Saturn. It's just that amazing. Now, coming back to the evening sky, so what can we look for? Well, on the 6th, the moon is just about 2 degrees below Venus in the southwest. So right after sunset, if you go out on that day, look in that direction. And if you have your cell phone ready, take a picture of it. It's a beautiful sight. The next day, the moon scoots up a little bit further away from Venus and is just below the planet Saturn. This is a great opportunity to see Jupiter, Saturn, Venus, and the crescent moon all together at the same time. So now on the night of the 13th to the morning of the 14th, the annual Geminid meteor shower occurs. So the peak hour is roughly in the early morning on the 14th. The Geminids radiate from the constellation of Gemini to Twins near the star Castor. And so under a clear dark sky, up to 150 meteors can be seen per hour. That's kind of the expected rate, although most of the meteors are faint and you really need a dark sky to see them. But there is a significant fraction of meteors that are bright, so it's worth watching. The only issue for this time is that the waxing gibbous moon will hamper observations until it sets up around 2:45 Pacific Standard Time on the morning of the 14th. A quick look at our evening sky, around about 9 o'clock mid-month. Jupiter is slowly sinking to the southwest. And if we look above Jupiter, just high in the southwest, there's a constellation called Pegasus. And the main stars are these four, which I circled here. If you join a line between each of these stars, that forms the shape of the Great Square of Pegasus. And below that are some faint stars that form the constellations of Pisces, the fish, and Aquarius, the water bearer, which are hard to see from our light polluted cities, but that's a challenge there. But if you're in dark sky, you can see these constellations. This region of the sky represents the autumn sector of the sky. And in contrast, if we look to the southeast, we see a region of sky containing many bright stars and stars that form the winter constellations, such as the most recognizable one of all is Orion the Hunter, which is represented by 3 stars in a row, and that's the most recognizable part of it. And then there's 2 stars above it, which represent the shoulders of Orion, and 2 below for his knees. Between Orion, just above it, is Taurus the Bull with its bright star Aldebaran. And the brightest star in the night sky, Sirius, is in the constellation of Canis Major, the Great Dog, which is directly below Orion. And you can find it by just drawing a line straight down from the belt, and you'll find Sirius in the southeast. And talking about winter, the December solstice kicks off the start of the winter season. So at 7:59 a.m. Pacific Standard Time, the sun rests on the most southern point on its annual path around the sky. This path is known as the ecliptic. It's represented by the red line in this diagram. The motion of the sun along the ecliptic is caused when the Earth moves around in its orbit around the sun, making it appear that the sun travels around the sky along the ecliptic. At local noon from Los Angeles, the sun is about 34 degrees above the south horizon. And this is the lowest noontime altitude for the entire year, as seen from Los Angeles. On this day, we have the shortest day of the year and the longest night of the year. With the summer solstice also marks the beginning of winter in the northern hemisphere and the beginning of summer in the southern hemisphere for all our southern neighbors. Looking into the morning sky, switching our view there, Orion and Canis Major are low in the southwest, and they begin to set at dawn. As dawn begins, much higher up to the south are the spring constellations of Leo the Lion and Virgo the Maiden. And that's a preview of the spring sky if you're up early in the morning. Our moon phases this month. So what do we have? We have a new moon, which occurs on the 3rd. First quarter is on the 10th. Full moon is on the 18th. And last quarter is on the 26th. And on the last day of the year, there is a special treat in the early morning sky. If you're up around about 6 a.m., look to the southeast for the 27-day-old waning crescent moon. And right below it, roughly about 2 degrees, is the planet Mars, the red planet Mars. And then next to that, to Mars, is the star Antares, which is in the constellation of Scorpius the Scorpion. It makes these three objects make an equilateral triangle. And if you look at Mars and look at Antares, they're almost the same color. And that's because Mars is, and Antares, I should say, is a name derived in ancient Greek that means rival or equal to Mars due to the color being similar to the planet Mars, as known to the Greeks. So this is a special treat in the early morning on the last day of the year. Get up to see that and stay up and see the new year through and enjoy.
Yeah, you might want to get up early, come into Griffith Park and go for a hike early in the morning and get a shot like this from the hiking trails. Normally the park does open a little before 6 a.m. The gates do, and you can get up into the park and go for a beautiful hike. Just be careful that it could be a beautiful sight to do on the last day of the year. So thank you for that, Patrick. Always fascinating to find out what we can go observe. Well, Chris, we're going to end tonight's show with you and finding out what's out to launch tonight and what we ought to be taking a look on. So what do you have for us to finish out our show?
Oh gosh, Griffith Observatory Launch Control is plenty busy monitoring an awful lot of things. We got lots going on. First of all, a little bit of a follow-up, something we talked about last month and indeed the launch the month before in October, because on October 16th, a mission we've referred to already this evening, Lucy, the mission to the Trojan asteroids way out by Jupiter, very exciting mission. They launched, but they had a potentially problem with the solar panels. Now, we talked about that in October. In November, I mentioned that they were looking at this carefully and possibly going to have some meetings about it. They've met, and they do think possibly one of the two unfolding solar panels is only about 90% deployed. Now, actually, it turns out that's all right. There's enough power into the spacecraft, so Lucy should be fine. NASA is happy with what they're seeing from it. The instruments have all been turned on the spacecraft and are performing as expected. So Lucy, I can now kind of put you to rest on any worries you had. Lucy seems to be doing just fine, and she's on her way. I mentioned Rocket Lab here. Rocket Lab is another example, like SpaceX, of a relatively new company in the space business, and they also have been launching vehicles to orbit. The Rocket Lab space launchers are smaller in size, but they've been wanting to start experimenting with reusability, which is, of course, what SpaceX has pretty much perfected with their larger Falcon rockets. The Electron rocket, though, the Rocket Lab, to come back, it doesn't have the size and the fuel capacity to come back under power. So how in the world could they find a way to reuse it? Well, they came up with a daring process, really. It's they essentially let the rocket fall back. It's designed to survive coming back down through the atmosphere, and then deploy a parachute. Now, you see here on November 20th, they did indeed have a successful splashdown of the rocket, but you don't, this is just the first step. You don't want to have the rocket in salt water. It damages the components of the rocket. So what they're going to do as a next step, now that we've had this successful parachute landing, is to have a helicopter come by and grab the parachute while the rocket is still descending. This may sound a little far-fetched, but it has been done in the past to recover photography pods from satellites, Earth observation satellites. They would come down in a parachute and be caught by a helicopter. It has been done, but now we're going to try to do it with a whole rocket stage. So that's the next step for Rocket Lab, and they seem to be doing quite well with that. We've also enlarged the International Space Station a little bit here with the arrival of the Pershal module, which is a docking module. It's a docking node. It has been launched and it has arrived and docked successfully with the space station. In the picture there of it approaching the space station on the right of your screen, you can kind of see there are 4 flat faces around it. Those are docking ports where spacecraft, visiting spacecraft, can dock. This will greatly help the Russians in their sending resupply missions and missions with cosmonauts and so forth to the space station. Now, looking forward a little bit here, December 8th, we've got another Russian launch. This is a launch of the piloted Soyuz spacecraft, but it's not a standard mission of scientists and engineers to the station. It is being led by a veteran cosmonaut, but on board will be Japanese, 2 Japanese people, in particular, Yusaku Maezawa. Mr. Maezawa is a very wealthy man. He has purchased this flight for himself and an assistant to spend 12 days in space, and some of that on the International Space Station. This will be his first space flight, but he's been planning to go into space for some time. And you may remember the name and recognize the face. In the center picture, you see him with Elon Musk. He actually talked to Elon about putting together a crew of actually artists. As a professional artist, I have to appreciate this. Artists, musicians, poets, what have you, and fly them around the moon, not landing, but fly them around the moon on that new giant Starship booster, that rocket that Elon is developing. Now, Starship is not ready yet, but Mr. Maezawa is going to fly to the ISS, and that will actually serve as training, hopefully, for a later flight to the moon. I hope it happens. We do have a science mission coming up, I should mention. The IXPE mission, this is a NASA X-ray polarimetry telescope. What polarimetry is? This is obviously looking at the X-ray wavelength. But these 3 telescopes out on the end of this spacecraft are going to look at X-rays in a particular way. You probably have heard about polarized light. Polarized light is when the oscillations of the light, or the energy in this case, are lined up in a particular way. In this case, that happens when the energy is subjected to strong magnetic fields. It's diagnostic of the processes that are occurring in things like, well, black hole accretion disks, active galactic nuclei, around neutron stars, and so on. So just sensing the polarization of the X-rays is very important. And that's what this vehicle is going to do. It's yet another space observatory. And it's going to be launched on December 9th. It's actually December 8th our time, I should point out. The beginning of the launch window is about 10 p.m. our time, but the launch window extends over the midnight boundary into the night. Well, just that's a stay up late opportunity to see this launch from Cape Canaveral. There's a cargo mission coming up to the International Space Station on December 21st. That's going to be another SpaceX mission. No people, just lots of cargo. And who knows, maybe some Christmas presents. And then the obvious, the 900-pound gorilla in the room, the JWST. As we mentioned, no earlier than the 22nd of December. It's intended to be launched that night. And I do mean night, meaning dark. For us, the launch time is 4:20 a.m. Pacific, but I have absolutely no doubt that all my astronomy friends, including the professionals like Dr. Reitzel and our guest, will be staying up late, right? We know where you're going to be that night. This is the launch of the year. This is the launch of the decade. This is a really important one, December 22nd. One quick note on, we talked about Starship and the big giant rocket that SpaceX is testing down in Boca Chica, Texas, South Texas. It hasn't flown in a little while. They have done some tests on the ground. You see one of them on the left of your screen of the second stage. These are all powered by the Raptor engine, incredibly powerful engines you see on the right of your screen. You may have just heard, it happened in the last day or two, Elon Musk was apparently concerned and passed around some internal memos at SpaceX that maybe the production rate of the Raptor engines was not what he needed. And he said the company could even get into financial trouble if they can't produce a lot of them. So they're having an all hands on deck increase in the production rate. I wouldn't be concerned. I'm sure SpaceX is going to be just fine. But you do have to remember the bottom stage of that rocket doesn't use one Raptor. It uses 29. So if they're going to be building lots of these vehicles, they are going to have to step it up and turn out a lot of engines. So that's going on. And while we're talking big rockets, also in this class, the only other rocket on Earth in this class is the SLS, the Space Launch System, not a SpaceX rocket, a NASA rocket. It's actually already been fully assembled out at Cape Canaveral in Florida, and they're going to be doing increasing tests. This is not going to carry a crew, but the system is designed to carry a crew. On Artemis 2, they will carry a crew around the moon, okay? Our first return since 1972, it's a big deal. But Artemis 1 will send this vehicle, the Orion spacecraft, all the way out around the moon on a test flight without people. I want you to just keep it on your radar. We're looking at potentially a February moonshot. Now that's plenty. It's a lot to think about, but for now, we're going to be keeping our eyes on South America, December 22nd, and the amazing launch of the James Webb Space Telescope. Back to you, Dr. Reitzel.
Yeah, thank you, Chris, for that. Indeed, JWST is the one we're all going to have our eyes on. I know I'll be up that morning. Whether I go to bed or not, we'll see. And, 10 years ago, I probably would have said, I'll just stay up all night. But now I'll probably try and get some sleep in the middle of the night. We're not doing anything special at Griffith Observatory, unfortunately. The middle of the night just a little too hard. But we will, of course, bring you updates about how it went at the next All Space Considered. We're looking forward to that already. The next one is on January 7th. We're not taking a break in January because it's far enough away from the new year. We'll all will have recovered from our celebrating. Please do follow us at all our social media here. Reach out to us if you have any questions or concerns. You can write to us on Twitter. Send us your beautiful astrophotography. Follow us on all the social media. It's always fun to hear from folks. Once again, Griffith Observatory, this beautiful view with Los Angeles in the background. We are owned and operated by the City of Los Angeles and the Department of Recreation and Parks. We love all the support we get from Griffith Observatory Foundation as well. I saw a bunch of donations came in tonight. Thank you everybody that made every donation. Every bit helps. They help support our school program for 5th graders that we've been running online at the moment. They help provide support for programs like this one tonight. The equipment we use to stream this comes from our foundation. So a bunch of thanks to them. Again, thank you, Patrick. Thank you, Chris, for joining us. And thank you, Jeff, Dr. Jeff Blake from Caltech. A wonderful presentation on the web and more in the future. And as always, I'm David Reitzel, Dr. Reitzel from Griffith Observatory. And thank you all for joining us tonight. And thank you to our tech crew. Want to do a shout out there to them, by the way. Wonderful job, Matthew and Brendan in the booth. And thank you to all our moderators on the stream tonight and to everybody that joined us with tonight's program. And we'll see you next month. Thanks again.
Everyone.